All right, let's jump right in. Today, we're diving into a world that feels like it's straight out of science fiction, but I promise you, it's happening right now. Physical AI and humanoid robotics. This isn't just about making software smarter, it's about giving that intelligence a body, the power to move, to learn, and to interact with our world in a way it never could before. It's going to be a fun ride. Where intelligence becomes physical. You know, this line just says it all, doesn't it? We're talking about the moment AI climbs out of the cloud and starts walking down your street. It's the shift from an algorithm that just crunches data to a robot that can actually pick up a tool and build something. This is the bridge, the connection between the digital world and the one we all live in. So, what is physical AI really? Well, for decades, AI has been kind of trapped, right? It's been stuck inside our computers, getting really good at games and sorting through spreadsheets. Physical AI is what sets it free. It gives that intelligence eyes, hands, legs. It's all about building systems that can actually see what's around them, think about what to do next, and then physically do it. We're going from bits and bytes to atoms and actions. Now, building these kinds of intelligent machines, well, it takes a pretty incredible set of tools. So let's open up the toolbox and look at the essential pieces you need to bring a modern robot to life. Okay, first up, at the very heart of almost every modern robot, you'll find ROS2, the Robot Operating System. The best way to think about it is like the robot's central nervous system. It's this amazing open-source framework that lets all the different parts, the motors, the cameras, the sensors, all of it, talk to each other without a hitch. It's the universal language that turns a pile of hardware into one single coordinated machine. Next, we have this brilliant idea called the digital twin. Look, before a robot ever takes a single step in the real world, it's already taken millions of them in a virtual one. We build a perfect digital copy of it in a simulator, like Gazebo or Unity. This digital twin is like a safe little sandbox. You can train the robot, test it, even crash it 1,000 times, and it doesn't matter, because there are no expensive, real-world consequences. It's a total game changer. Of course, for a robot to be really useful, it has to get what we're saying and see what we're seeing. That's where vision language action models, or VLAs, come in. They're amazing. They use computer vision to see the world, language models to understand a command, like, hey, can you grab the red block? And then they figure out the action needed to make it happen. It's this beautiful blend of seeing, understanding, and doing. Seeing the world is one thing, but actually moving around in it with any kind of skill, that's a whole different challenge. And that's the job of control systems and dynamics. This is the science that lets a robot balance on two legs, walk without falling over, or pick up an egg without crushing it. Honestly, it's what separates a clumsy bucket of bolts from a machine that moves with real grace and purpose. And all of this, everything we've talked about, it all leads to this one ultimate goal: embodied intelligence. We're not just talking about a robot that follows a script. No way. This is about creating a robot that can actually learn from what it does, that can adapt when it's in a new or messy place, and that can operate all on its own. This is the moment where the intelligence truly becomes physical. So, you've got all these amazing individual parts. How in the world do they come together to create a robot that actually works? Let's walk through what a typical development journey looks like, taking an idea from the first line of code all the way to a walking, thinking machine. You know, the path is actually pretty logical when you break it down. You start with the foundations, right? The first few weeks are all about setting up the basics, like Rust 2 and getting your simulation running. Then once you have that, you focus on movement, navigation, and control, teaching the robot how to get from point A to point B. After that, you give it its senses, integrating AI so it can see and understand. And then the grand finale, you put it all together, integrate everything, and deploy it on the actual physical robot. Now, I've got to say, one of the single biggest challenges in robotics today is crossing the bridge from the virtual world to the physical one. People call it the sim-to-real problem. Nailing this transfer is absolutely key to making robots that work. So, the sim-to-real workflow usually has 4 big steps. First, you get your development environment all set up. Next, you configure the actual physical robot so it perfectly matches the virtual one. The third step is where most of the magic happens. You simulate everything, testing and tweaking until it's perfect. And only when it's absolutely flawless in the simulation do you do the final step: deploy the code to the physical robot. It's a safe, smart way to build. So, how do you make sure all this complex stuff actually works? Well, it's not just one thing. Development relies on a bunch of different checks. You've got your theory, which you test with quizzes. You've got practical skills, which you prove out in those simulations. Collaboration is key, so peer reviews make sure everything works together. And finally, the big test, projects that prove you can bring it all together to do something real. So after going through this whole journey, what's the payoff? What incredible things can a system like this actually do? Let's look at the skills that really define a state-of-the-art intelligent robot. What you end up with is pretty amazing. You have a system that truly understands the fundamentals of physical AI. It's got total mastery over its core operating system, ROS2. It's an expert in using simulation workflows and is ready for the unique challenges of humanoids. It can run these incredibly complex vision, language, action systems, and, most importantly, it has made that critical leap from simulation to reality. That's a toolkit for the future, right there. So I want to leave you with a question. We've looked at the tools, we've walked through the process, and we've seen the unbelievable potential here. We've followed the path from a single line of code to a thinking, moving machine. Now, the real question is, what problem would you solve with a physical AI? Think about it.